All right, welcome to Calculus 2. This is the first chapter that we cover in Calculus 2, Chapter 6, where we're looking at some applications of integration. In this class, we look at several applications of the integral. Some of them appear in this chapter, Chapter 6, and some of them will appear later in Chapter 8, when by that time we will have learned more integration techniques that are going to give us some tools to tackle those sorts of applications when we come across them later. But before we get into this section here, where we're looking at the area between two curves, I want to do a very brief review of what the definite integral is, which you should have learned towards the end of Calculus 1. So basically, in Calculus 1, you're taught that a definite integral is a way of determining the area beneath a curve. And what we mean by that is the area between some curve, which is given by a function y equals f of x, and the x-axis. We interpret that area as positive if the area is above the x-axis, or if the curve is above the x-axis for that portion that we're finding the area. And we interpret that area as negative if the curve dips below the x-axis, so we have area going below it. You talk in Calculus 1 about how to approximate this area before you find an exact answer to the question of finding this area under a curve. And you do that by using what's called the rectangular approximation method, which is what's shown here. So the idea is that if we're trying to find the area beneath this curve, y equals f of x, over some interval on the x-axis, say a, b, then we can approximate that by breaking that little interval up into small subintervals. And if we make each of those subintervals have the same width, we could call them each delta x. That's the width of those subintervals. So that gives us one of the two dimensions of each of these rectangles. The width of each rectangle is delta x. To find the area of a rectangle, it's width times length, or we could think of this as height as well. So the height of each of these rectangles is determined by choosing some sample point within each of these little subintervals, plugging it into your function y equals f of x, which would then take you to a point on the curve. The y coordinate of that point, which is what we get from plugging our sample point into this function, tells me the height of each one of these curves. In this example, all of the sample points were chosen to be the right endpoints of these intervals. You can see them here, but there's no rule saying that that's how that has to work. You can choose any sample point within any one of these subintervals that you want to, and we tend to denote those by xi delta star. Or I'm sorry, xi star, not delta star. The I indicates which subinterval it came from. So x1 star means it came from the first subinterval, and so on. If you add up the areas of each of these rectangles the way that we discussed, then you get an approximation for the area under the curve. And we see in Calculus 1 that the more rectangles that you're able to cram under this curve, the better that approximation is going to become. And then we can take that idea from an approximation to an exact area by applying a limit to it. And that's what this is right here. So on the right-hand side here, I have a sum, which is indicating that we're summing the areas of each of these rectangles. And then I have an expression in here which represents the area of each rectangle for each I that I can plug in there. Remember, the delta x is the width, the f of xi star is the height, and so the product of those two things gives me the area of each rectangle. If I take the limit as n goes to infinity, and notice where n shows up, it's up here, it's the top of the sum, that's indicating how many rectangles I'm cramming into this little region here. So if I let the number of rectangles go to infinity, then this takes this thing from an approximation to an exact area, and now I have something useful. I can tell exactly what that area is. That's what we call the definite integral, and that's notated here. So none of this is new, right? You spent however long at the end of your Calculus 1 class doing this, but I wanted to go over that review because this once we learn how to compute integrals, it's common for students to kind of fall away from this derivation of the integral. They start to kind of not necessarily forget how the definite integral was defined, but sort of lose sight of the importance of this. And the reason I bring this up now is because integrals, as we're going to see throughout this class, are used for far, far, far more than just finding areas under a curve. In fact, in practice, that's one of the least interesting or least useful applications of the integral. We use the integral for all kinds of things, most of which have nothing to do with area at all. So the reason for that is because this idea where we're summing up things that look like products, where I have a subinterval whose width is delta x and a function y equals f of x that I'm choosing sample points in and plugging them in and doing this whole thing, that can be used to represent something other than just areas of rectangles. That can be used for all sorts of useful things that we're going to come across. So every time we introduce a new application of the integral, we want to keep in mind this thing here. We call this a Riemann sum. Okay, that this is where the definite integral comes from, and understanding this definition helps to motivate a lot of the applications that we're going to see. So the very first application we're looking at actually does still concern area, and this is area between two curves. So the difference between this, what we're doing in this section, and what you did at the end of Calculus 1, where you were introduced to the definite integral, is that we're not just looking at the area between one curve in the x-axis anymore, but now we're looking at the area between two different curves. And so how might we use the integral to come up with that area? Well, let's just say that we have these two curves here, y equals f of x and y equals g of x. F of x is the red curve, g of x is giving me this blue curve here, and I want to find the area of the region trapped between these two curves over this interval from a to b. Okay, in this context, when we're talking about the area between two curves, we're always going to be interpreting the area as positive. So even though the definite integral can give you negative values, this application should only give us positive values. And in fact, if you get negative answers from the types of problems we do in this section, that's an indication that you did something wrong. So we'll talk about that in a second. How do we come up with this area between two curves here? Well, what I'm going to do is something very similar to how we derived the definite integral. I take this interval a, b, and I want to divide it up into subintervals, and over each one of those subintervals, I'm going to construct a rectangle, okay? And I'm going to find the area of that rectangle. Now, the width of each of these subintervals that I choose will still be delta x, the same thing that we used up here, okay? It's the height of the rectangle that's a little bit different now. So, as before, in any given subinterval, let's say that this is the ith subinterval right here. In any given subinterval, I'm going to choose some sample point, which I call xi star, and then I'm going to plug it in. But I'm not going to just plug it into f of x. I'm also going to plug it into g of x. See, if I plug that xi star into f of x, it's going to give me the y coordinate of this point up here. But then if I plug xi star into g of x, it'll give me the y coordinate of this point down here, because that's where g of x is. Okay, and I can see that the largest y coordinate for the point way up here minus the y coordinate down here should give me the total height of that blue dashed line right there. That's the height of the rectangle. So the key here is that the height that I want to multiply my delta x by is f of xi star minus g of xi star, because that difference is now what's giving me the height of that rectangle, okay? So I would do that for each of these rectangles that I construct over each of those subintervals, and for each one, I'm going to have f of xi star minus g of xi star as the height, and then delta x as the width. And so computing all of those areas, and then summing them up gives me a Riemann sum, but it's going to look like this, okay? From our definition of the definite integral, taking this limit here as the number of those rectangles goes to infinity would take me to this integral right here, okay? And so this is what we're going to be using to compute areas between two curves. Now, you need to be really, really careful with this. The number one place where people are going to go wrong in this section are confusing which function goes where. Remember, subtraction is not a commutative operation. What that means is you cannot switch the order of a difference, of a subtraction problem, and get the same answer. If you switch the order, you'll get a different answer. So it really matters which of these two functions goes first and which one goes second. Notice f of x shows up first, and in this example, f of x was the highest of the two functions. G of x was the lowest. So we want to think of this as high minus low, okay? Let's do an example. So here we're looking at an area problem that says find the area between the curves y equals 1 plus x cubed and y equals 2 minus x from x equals negative 1 to x equals 0. Okay, notice that the problem does not tell you which function is the high function and which one is the low one. We know that we're going to have to subtract these two, but the order of subtraction is the thing we have to figure out first. And this is where it's really, really important that you have a very firm grasp on how to graph functions by hand. Okay? We don't actually need to be super accurate with our graphs. There's just a certain amount of detail that we need. So I'm going to try to graph the two functions given here. Okay? So let's think about this for a second. The first one, y equals 1 plus x cubed. So that looks like a cubic function. Now I know what y plus x cubed looks like. It's got kind of this sort of sideways S sort of a shape, if you can picture that. But it's not y equals x cubed, it's y equals 1 plus x cubed. So actually what that would do is it would take that cubic function and shift it up 1 unit. So it's actually going to look like this. And I'm not so concerned about my graph being perfect here. I just need it to be generally what the graph of that function would look like. The cubic function normally intersects the origin, but since I shifted this up 1 unit, that would be a 1 right there. That's where it's intersecting the y-axis. So that's going to be my graph of the first function. That's y equals 1 plus x cubed. How about this second graph right here? Y equals 2 minus x. So if I ignore the 2 for a second, I have y equals negative x. That's a line through the, that's a line, well, actually, I'm going to take that back. I don't want to ignore the 2. Let's just think of this the way we would normally think of it. I can rewrite this as y equals negative x plus 2. That's a line in slope-intercept form where the y-intercept is 2. Let's put that right here. And the slope is negative 1. So that means that the slope, or the curve, the line rather, is going to be going downhill as I go from left to right. So I would sketch something like this. That's the line y equals 2 minus x. Okay? Now, did I take special care to make sure that this line had exactly a slope of negative 1 relative to the way that I sketched my axes? No. It's not a huge deal that I make it the exact steepness if I'm doing this by hand. Really what I'm trying to get from this graph is a way of determining which of these curves is on top and which one is on the bottom. And in addition to sketching them, it's also important to take note of what interval I'm looking for this area over is. So we're looking at the interval from negative 1 to 1. Now, see if you can determine that negative 1 is exactly where my cubic function is going to be intersecting the x-axis, okay? Should be pretty easy to see why this would be negative 1 right here. 0 on the x-axis, of course, is right here. It's the origin. So we're looking for the area between these two curves, between here and here. It's this region that we're looking at, okay? I want to shade that in because depending on where this region is, different curves can be on the top and different curves can be on the bottom. So the way that I'm looking at this, the y equals 2 minus x line, that graph, is the high function, and the y equals 1 plus x cubed, my cubic function, is the low one. It's on the bottom. So the way I would do this integral, I would set it up as the integral from negative 1 to 0. Then I take my top function, which is 2 minus x, and then subtract my low function, which is 1 plus x cubed. Here is the second most common mistake people are going to make in this section. It is super important that you put parentheses around your functions as if they have more than one term in them. If this was just a negative x, I probably would have left the parentheses off. In fact, the parentheses around the first function are not really that important. It's this second one that's really important. And the reason it's super important to put parentheses here is because that minus sign needs to distribute to everything in this set of parentheses. I'm subtracting the entire function, not just the first term of it, right? People forget this, I've noticed, all the time. And then they get really confused as to why their answers are coming out incorrect. It's because you didn't put parentheses around that second function and then distribute the minus sign. So before I do any integration, I'm just going to simplify my integrand here. So paying attention to what would happen with this minus sign, I'm going to have 2 minus 1, so that's 1. I'm going to have negative x. There's no x terms in here for that to combine with, so that's going to stay negative x. And then I have a minus x cubed. See, that's where the parentheses mattered. If I didn't keep those parentheses, I probably would have kept that a plus x cubed, and that's going to give me a wrong answer. All right, so now we do the integration by finding an antiderivative of that function there. That's going to become an x minus x squared over 2 minus x to the 4th over 4. I am trusting that you are comfortable with finding the antiderivatives of polynomials and simple functions like this, because you should have spent plenty of time in Calculus 1 doing that. I'm not going to review that here. Okay, next up is a definite integral, so I need to take this upper limit of integration, plug it into my function, and I can see that I'm going to get a 0 everywhere that I do that, so the whole thing's going to come out to 0. And then I need to subtract whatever I would get from plugging negative 1 into each of these terms here and summing everything, right? So put a set of parentheses around this as well. If I put a negative 1 in for x, that's negative 1. If I plug negative 1 in for x squared over 2, that's going to be 1/2, so I have minus 1/2 here. And then I'm also going to end up with minus 1/4 there when I plug that negative 1 in, okay? Notice that each term is negative here. If I do negative 1 minus 1/2 minus 1/4, that's going to come out to negative 7/4. But then this minus out here is going to change that negative to a positive 7/4. That's going to be the area between those two curves over that interval. Notice this is where we do something called a sanity check. There's plenty of opportunities to do these all throughout this class and most math classes. A sanity check is something that you do when you are working through a problem and you get an answer and you just want to make sure that the answer that you're getting makes sense in the context of your problem. And the sanity check that we use in this section is we need to make sure that our areas come out positive. Like I said before, the answer to all of these problems should come out positive. We should not get negative areas here. Okay, so I got a positive answer. Does that mean that I'm absolutely correct? By itself, no. This is the correct answer, but my sanity check is not going to tell me for sure if I'm correct. It's just a quick way to see if I did something wrong. So no red flags are going off here. I feel good about my answer. I'm going to end this video here. We'll do some more examples in the next one.